Hey, Physics 30. So, on to lesson 4, graphing for profit and pleasure. All right, so what this is going to be is about it's literally what scientists do to actually come up with a lot of the equations that we're actually using. It's really taking a real world situation where the scientists would be gathering data and then using that data to figure out some sort of variable or some sort of constant. So I'll show you what that means. This first part, they kind of go over the basics of graphing. I'll let you guys look through that. We've done a lot of that in the past, so just make sure that you know those points. But I think more than anything, I'm just going to give some examples here. So, first one, a more straightforward example, which kind of sucks because it's on 2 different pages. But if let's say scientists were given the data for the height of something and the energy that it got based on that height, then we could graph that, right? So what that would look like if you graph that data is it would look something like this, right? And you get a straight line going through it. Yada. So what this means though, like what we can do here is if we start off with the equation E is equal to mgh, right? So that's potential energy is equal to mgh. And then what this whole lesson is going to be about is I want to rearrange this in such a way that I have something over something, right? Like E over H. And the reason why I want something over something is that really resembles our slope is equal to rise over run formula, right? So E here is my slope, and H is my, or sorry, not slope, is my rise, I mean. E is my rise, and then H is my run. So that makes sense, right? So if I just have E, right, rise over H, my run, then when I graph this thing, it should give me a straight line, right? As long as you have something over something, that's going to give you a straight line. Maybe I'll just kind of explain that a little bit better, though. If this was like, it's not, but let's say it was like H squared, though, then you wouldn't get a straight line, right? If it was a squared. But I'll show you how to deal with something like that in a minute. So one thing I just want to kind of want you guys to know this here when we're looking at this, just for make sure you're graphing these things correctly. So here's all your points, right? So point, all the way up like that, right? And then these x's here, what these x's represent is when you actually figure out what the slope of your graph is, you want to connect it to the graph in a place that isn't a point. You know what I mean? So if we like turn this into a triangle, this wasn't I wouldn't actually connect it to that point because I'm kind of running, part way between the line here. but that's the idea, is that where I connect my triangle to here to figure out my rise and my run shouldn't be actual data points. They should be different points on the line. So that's what that is, right? So, okay, moving on. All right, so, and then the idea here is that once you figured out what that slope was from the graph, right, figuring out your rise over run, then you could go back and say, well, okay, if I know my slope, then we said, sorry, I'm kind of scrolling all over the place. We said that the slope part of this formula, right, the slope part of the formula was mgh, right? That's what the slope is. Okay, so if we go down here, then I can say, well, slope is equal to mgh. So then, if that's the case, if I figured out my slope was 26.1 joules per meter, just from the graph, right, just figuring it out, then that would just be over 9.81, right? Just rearranging this equation for m, if we were trying to find m in that case. Okay, so this is like a pretty direct example right here, but let's move on. So I'll kind of show you some different examples. So in this case, the following data relating kinetic energy and speed was recorded. So here's speed, here's kinetic energy. So I might say, well, okay, EK is equal to 1/2 mv squared. And then I'd be saying, okay, so that's good. I've got speed, I've got V, right? I've got energy. And if I was looking for mass, then let's just rearrange this thing a bit. I could rewrite this as EK over, actually I'll call it 2EK over V squared is equal to m, right? Just rearranging that equation. Now, so I've got something, and you might say, okay, well, there's my rise. Actually, you know what? I could do that. I'm going to leave the 2 down here. I'm going to leave it over there and say this is equal to my slope. It'll just make it a little less complicated. So anyway, yeah, so I could say EK is my rise, so that's good. So that's my rise. Sorry, that was terrible. And then V squared is my run. V squared is my run. So speed's not my run. V's not my run. V squared should be my run. So what we're going to have to do here is I can still get a straight line into this, but I'm going to need a new column. You're going to need one more column with a V squared. So what you would do is you go through each one of these and square them. And then that's what we're going to plot. So we would actually plot, right? Because here, this is EK versus V, right? That didn't give me a straight line if I just plotted that. But if I made a new column for V squared and plotted EK versus V squared, I now get a straight line, right? And I can now figure out my rise over my run, using my two different places on the line, figuring out I have a slope of 2.4 kilograms. But remember, like the way I had it written there, I had EK over V squared is equal to M over 2, right? Or 1/2 M, right? So that's my slope. So I still need to, in the end, if my slope is what I figured out there, then I still need to multiply that by 2 to figure out what my mass was. Okay, so that's the gist of it. Yeah, let's. And here's another little one, just another little trick one here, where. So for this one, we've got power and we've got time. So you're just going to look to your formula sheet and figure out which of those has, power, time, and is looking for the work done. So in the end, it's this one, right? But if I go power against time, right, or power versus time, you end up getting a graph that looks like this one, right? And that's not a slope. I can't figure out the slope of that graph. I really need something, right? I need rise over run. I should say slope. Slope is equal to rise over run, right? That's what I'm after. So I need some sort of way of turning this into something that looks more like this. And here's a little trick we're going to do. We're going to say work is equal to P. And then I need it to be over something. Well, multiplying by, or let's say it this way. So dividing by a fraction, the same as multiplying by the reciprocal. We're going to do the same type of thing here. So I'm going to call it 1 over T. Right? Because if you maybe it's easier to think about the other way. If I flip that around, right? If you're dividing by a fraction like I'm doing there, that would be the same thing as going P times T over 1, right? Or what we started with, right? Same thing. So hopefully that made sense. So that's a little trick we're going to do. So now I'm going to need another column that is 1 over T. So what I'm going to have to do is every one of these things in the time column, I would make another one that would be 1 over time, and I'd just go 1 divided by 2, 1 divided by 4, 1 divided by 6, and make a new column here. Okay, so that's the idea. So you can see that here. That's what that's what this is. S to the negative 1. That means 1 over T, right? That would be the unit. And if you do that, you do end up indeed with a straight line. Okay, so then everything from there would be very similar. So in this case, it was just equal to work when you find the slope. All right, so that's the gist of it. Let's do some practice problems here. So the following data was generated experimentally to determine the coefficient of friction for a horizontal surface. Using a suitable graphing technique, find the coefficient of friction for the surface. Okay, so what I would do, look to my formula sheet, and I'd be trying to find things that had Fn, force of friction, and our coefficient of friction, which was the symbol mu, right? That was that one. Okay, so there's really only one there. That is the force of friction is equal to mu times Fn. So if I want to figure out what mu is, I'm going to rearrange this. So I would write it as mu is equal to force of friction over Fn. Okay, So now if it's written like that, force of friction is my rise, Fn is my run. So that's really telling me what's going to be my y and x, right? This is my rise. This needs to go on the y-axis, and this needs to go on the x-axis. Okay, so let's figure out a suitable scale here. So force of friction first, 'cause that's going to be my y. That goes from, I'm going to start at 0, and I need to go up to like 5, right, or 4. We'll see. So if I'll look at what I kind of have here. So if this is 0, I'd really like this to be 1, 2, 3, 4. This last point is 4.2. You know what? For this case, I'd actually just leave it like that. I wouldn't try to change the scale drastically on that one, just because this works out so nice with these big lines being 1, 2, 3, 4. I'll just put this point a little bit above the top here, right? When it comes to it. Okay. And then Fn needs to go from 0 to 12. So what I'm going to do on the bottom here, I've got 1, 2, 3, 4, 5, 6, 7. So I think if I go up by 2 for each one of those big ticks, I should be good. Actually, I will be good. All right, so we'll go 2, 4, 6, 8, 10, 12. Okay, and then let's do our axes, right? So we've got Fn, capital N, in newtons. And on our y-axis, we've got force of friction, which is also in newtons. Okay, so now we need to plot our points. I'm just going to pause it and plot my points, and hopefully you guys can do this as well. So pause it if you guys need to, and then maybe do these yourself. Okay, so there's my points. Hopefully you guys were able to get something similar. And then now I'm going to make my line of best fit. So this is where you would need a ruler. Hopefully you guys have a ruler. I'll make sure you guys have rulers today. Draw. All right. Straight line here. So I'm going to do my best here. So you'd start right at 0. Oh, this isn't going to work great. Oh yeah, that's not too bad. I ended up all right. Maybe. Come on. All right. So then I'm just going to make a line of best fit. Something like this, right? So it doesn't go through all the points, like right here, right? It doesn't go through that point. It's just the line of best fit. Then what we're going to do is we're going to find some points on the graph here where, and you know what I'm going to do is I'm going to pick a different color for first thing. Places where it kind of crosses nicely through the line here, right? So right there might be a good one, and right there, it really nicely crosses through, right? So then we can make a triangle out of this. All right, so now we just have to figure out the rise and the run of this thing. So looking at the rise here, let's figure out what we were at the top. So this was, at this point, it was, and even just write it here if you're not sure. So 3.8 is how high it went there. Down at the bottom, we were at 1.6. So our rise here would be, well, 3.8 minus 1.6, right? So 2.2. So it's going to be 2.2 for the rise. Okay, and then we're just going to do the same thing for our x, right? So here we're at 10.6. And then here we're at 4.4. See how it's nice how I chose these ones that kind of like line up right on these lines? Yeah. So we would end up with, so this will be 6.2 from there to there, right? Okay, so then in the end, so now we've got that. So we got our rise, our run. So our formula here, right, is just the slope of this thing is u, right? That's already written like in the form slope is equal to rise over run, right? Rise, run. So I just need to find the slope. Right, well, that's easy. So slope is equal to Our rise was 2.2, run was 6.2. So we've just got 2.2 over 6.2. And we get a coefficient, because that was also equal to the coefficient of friction. So the coefficient of friction ends up being 0.35. Okay, and there would be some error in that. Maybe your answer was a little bit different, right? But it should be close. It should be pretty close to that one. All right, I'm going to do one more just because they're kind of long ones. I'll let you guys do that one. I think I'm going to do... Nope. There is only one more, sorry. All right, I'll do this one with you. Okay, number 2. The following data was collected to calculate the constant K in the following equation. Okay, so you guys will see this one later on, right? We haven't done this yet. But E is the electric field strength, Q is the charge generating the field, and R is the distance from the charge. The charge used for this experiment was 2 times 10 to the negative 3 coulombs. So using a suitable graphing technique, find the value of K. All right, so what I would want to do here, if I want to find K, then we will, and we're given R and E, is I'd really just like to first get R and E over to the same side of the equation. So I'm going to move this R squared over there. So let's rewrite this as R squared times E. I'm just going to leave it like E for now, is equal to K times Q. Okay, I'm not going to bring the Q over there. I could, but then I'd have to like include that in every one of my columns, right? I'd have to multiply or divide everything by Q or whatever I did there. It's kind of easier just to leave it as part of the slope part of it for now, and then just figure it out once you've figured out, or get rid of the Q once you figured out your slope. Hopefully that made sense. All right, so right now though, I've got R squared times E, right? I need something over something. I need a rise over a run. So we can do a couple little things here. We can do a couple little tricks. And it doesn't matter which one you do, but do you remember how we turned it into like 1 over something, right? We're going to do that again, and I could change this to 1 over R squared, or I could change this to 1 over E. You'll get the same answer either way. What I'm going to do, doesn't really matter. I'll change it to 1 over R squared, just so that I've only got to make one more column, because maybe you'll see what I mean in a second here. So I'm going to change this to E over 1 over R squared is equal to KQ, right? So just look at this for a second though, to see if you can make sure this makes sense, right? If I divide by a fraction, that's the same as multiplying by the reciprocal. So this and this are exactly, they're the same thing. They're the same equation, right? So this is perfect because now I've got a rise and I've got a run. All I need to do though is change this into a column, right? I need to make a new column for that one. So let's do that. So what I'm going to do, make a new column for 1 over R squared. Okay. So that's what I'm going to take each of these R's and we're going to go 1 over the square of that. So here you can fill those in. I'm just going to pause it and do it. All right. So that's what I found were these numbers. Okay. So then let's graph. So remember I need E on my y-axis because it's the rise, and I need 1 over R squared on the run. So what are we going up by? So we got E goes from 0 to around 50. So let's see what we got. So I am going to go, and I'm going to do the same type of thing just because of the graph that they gave us here. I'm going to go 0, and I'm going to go up by 10s. 10, 20, 30, 40, and then I'm just going to go off the page for this one. Okay, and then the other one, I'm going to go up by 5. So 5, 10, 15, 20, 25, 30. Okay, so now let's plot some of our points here. So, yeah. So I got, what's our first one here? Sorry, I'm scrolling everywhere. So our first one is going to be at it's really our like first numbers here that we're going to start with, right? So 1 and then 1.8. Okay, so 1 and then 1.8 would maybe be around like there. And then the next one would be at around there. And 5. Shoot. Okay. Sorry, I just had to pause it there. I was kind of confusing myself. Oh. Okay. So, okay, we're going to make a straight line again here. Sorry, guys, I forgot to push record. Try to catch up to me here. Sorry. Pause it maybe if you need to and try to catch up here. I was talking for a while. Okay, yeah, so... Okay, once you catch up. Okay, so let's figure out. So we are at 34. It looks like right there, right? And then on the bottom, we are at, what are we at there? 16. Okay, so we've got 34 minus 16. So we're going to have a rise of 18. Remembering, I'm saying 18 here. I shouldn't be really doing that because this is times 10 to the negative 7 for each of them. But just for the sake of simplicity, we'll do that for now. That's one thing I forgot to do. I should have my axes there. I'll do it after. All right, so we got 18. And then for our rise, and then our run goes from, what's that? This is actually just 19 there, right? And then on the back side of this, we got 9. So it's going to make this easy. So we got 10. Okay, so then in the end, our slope is going to be 18 over 10, but not really because I didn't have my units right. So let's do that now. So our y-axis here for E, right? This was our electric field strength. And it was every one of these ticks was times 10 to the 7 newtons per coulomb. Okay, that's newtons per coulomb, sorry. And then our units for the bottom here are going to be 1 over meters squared, right? Because it's 1 over r squared. So this is 1 over r squared that we're doing here. And our units would be 1 over meters squared. Okay, so let's just write down what our equation was again now, right? We said that E over 1 over r squared was equal to KQ. Okay, well that means that KQ would be my slope in this case, right? So we just figured out, so we can figure out slope. So slope of this graph will be rise over run. That's going to be 18 times 10 to the 7 though, because those are my units, right? Newtons per coulomb over, and then that ended up being 10, which is nice. And then the units are 1 over r squared, or r to the negative 2 would be the same thing. So our slope would be (1.8) times 10 to the 7. And now I'm going to write my units a little bit different here because I've got r to the negative 2 on the bottom. That's like 1 over r. I'm going to write this as newtons times r squared, right? Because I could bring that up to the top, right? Because that'd be like 1 over r. So dividing by a fraction, same as multiplying by the reciprocal, over c. Okay, so those are my units so far. And then remembering that we said the slope was KQ is equal to 1.8 times 10 to the 7 newtons times r squared over coulombs. Okay, so now I want to find K, right? So my last thing that I have to do is just divide by my charge. So K is equal to 1.8 times 10 to the 7 newtons times r squared divided by coulombs divided by, and it gave us our charge at the beginning, right? It just gave us that number, 2 times 10 to the negative 3. coulombs. All right, so K is going to be equal to 9, let's say 9.0 times 10 to the 9. And its units are newtons per meters squared divided by, well, since we divided by another charge, coulombs squared now. So those would be my units. So we're going to deal with this quite a lot later on. This actually ends up being quite close. If you figure out your percent error, I won't go into that one, but it ends up being really close to the actual number. It's 0.1% error. That is how much that's off, right? Like, so very, very close doing it with this method. All right, so that's going to be it. Sorry for jumping around so much of you guys. Okay, we'll see you guys in class.